So I already kind of mentioned the term humidity. Humidity is just focusing on water vapor, and it's saying how much water vapor do we have in the atmosphere. There are all sorts of different ways to measure the water vapor in the atmosphere, and actually we're going to do one of them in the lab this week. But I need to focus on two types of three ways actually in describing how much water vapor there is in the atmosphere. And the first two are going to seem kind of foreign, and they're going to look very mathy, but just stay with me, okay? I need to talk about something called absolute humidity. They have to do with meteorology and kind of how we describe the water vapor in the atmosphere. Absolute humidity and mixing ratio. So it's best to kind of show you just a picture. So here's a picture of a chunk of air. It actually then, all of these water particles are in there. Oh, I didn't want to do that. All these water particles are in their gaseous state. So here we have water vapor. Okay, so now in this case, or let's just look at both the cases. Well, both the cases, they both have mass of the water. Okay, and the mass of the water, I'm going to show you two scenarios, and the mass of the water is going to stay constant. That's 20 grams. So we are going to plug in some numbers here, but just bear with me. Now, in the case of absolute humidity, we take the mass and we divide it by the volume. So in this case, it looks like we have a volume of 1 meter cubed. So 20 grams divided by 1 meter cubed, you can see that the absolute humidity is 20 grams per 1 cubic meter. I hope that works for you. So now here we have, what about mixing ratio? And actually we're going to stick more with mixing ratio here when we go to the last way of describing humidity. We're going to use mixing ratio to kind of piggyback from. So mixing ratio takes that 20 grams of water, and now we're going to divide by the mass of the dry air. Well, the mass of this dry air happens to be a nice number, 1 kilogram. So if you divide 20 grams by 1 kilogram, 20 grams of water vapor by 1 kilogram dry air, you get 20 grams per kilogram. That'd be grams of water vapor per kilogram of dry air. So I'm going to go ahead, and this is important because later on we're going to talk about how clouds are formed by basically a chunk of air lifting or rising. So here's my chunk of air rising, and hopefully what you can kind of see visually is, does it look like it got bigger? Okay, as a chunk of air rises, it will get bigger. Okay, and when I say bigger, basically it's going to occupy a larger volume. So let's go ahead and look at now the absolute humidity. Notice that we still have 20 grams of water vapor, but now we have a volume instead of 1 cubic meter of a 2 cubic meters. So that means if we take 20 grams of water divided by 2 cubic meters, now we have an absolute humidity of 10 grams of water vapor per cubic meter of air. So notice that this changed, okay, as the volume changed. Makes sense because it's relative to amount of volume. Now let's go down to mixing ratio, where mixing ratio was the grams of water vapor, which is still 20, okay, divided by the mass of the dry air, which did not change as the parcel got bigger. So notice that our mixing ratio stayed the same. So our mixing ratio again is just our 20 grams of water vapor divided by the mass of dry air, which is still 1 kilogram. Okay. So one last means of that you're probably more familiar with defining humidity is what we call relative humidity, or RH. Okay. So before I get to relative humidity, what I need to explain is this thing again about saturation. Remember, saturation was like the third box on the previous video, where basically the rate of condensation, the rate of evaporation is equal to the rate of condensation. This is gas and this is liquid. Okay, they're at equilibrium, and we call the air, they say the air is saturated. Remember, I also said that also means if the air is saturated, that's 100% RH. Okay, and a lot of times students kind of come with that intuitively, but how do we calculate that? Well, we actually have these. Let's see if I can clear this slide. We have kind of this. Oh, I know what I was going to say. At these different temperatures, also, do you remember that I said if you monkey with the temperature, you're more likely to get condensation. And I said if you cool, this is getting cooler, if you cool the temperature down, okay, I said you're more likely to get condensation. If you increase the humidity, if you cool it down, you're more likely to get condensation. Well, as you cool the water down, over here in this last, I'm sorry, not the water, well, the environment the water's in, if you cool it down, over here, these are saturation amounts, okay, given in mixing ratios. So basically, this is the max amount of water vapor at these temperatures. The air is what we say saturated. Okay, I hope that makes sense. And so, for instance, like if we're sitting here at 20 degrees Celsius, 68 degrees Fahrenheit, we max out at 14 grams of water vapor per kilogram of dry air. If instead we're at the freezing point temperature, 0 degrees Celsius, 32 degrees Fahrenheit, notice that our air can only hold, we max out at 3.5 grams of water vapor per kilogram of dry air. All right, so we end up then with being able to measure something called relative humidity. So relative humidity is a little ratio, it's two numbers, and in the top number we put what it really is, what the air is, and in the bottom number we put actually the maximum, we put saturation amount at that temperature. Okay, so I think I have I have some examples coming up. Okay, so in other words, and I think I kind of picked on two temperatures, in other words, if you're sitting at 20 degrees Celsius and you're at 14 grams of water vapor per kilogram of air, you are at 100% relative humidity. You have maxed out. And actually, the example I'm coming up with on the next part, we'll talk you through this, but let's just say instead of 14, let's say you only have 7 grams of water vapor per kilogram of air. Okay, so that would be what, your AC, that's what you actually have. Now, and if you are at 20 degrees Celsius, then your maximum is 14 grams per water vapor per kilogram of air. So of course 7 divided by 14, and I'm going to go ahead and get it in parts per 100, okay, that will give you 50% relative humidity. Does that make sense? You're halfway there. Okay, I hope so. And again, I've got some examples coming up.